For everyone, it's June 19th. Alright, first one today. Short encoding of words. So we kind of catch up of all the leftovers we had in the previous days. So maybe we can venture into another problem. Oh, going to page 47 now. I don't think we have finished page 46 yet. So I have to go to page 46. I should have opened this earlier. Now it'll take a long time to load. Alright, no, we still... Oh my god, look at this. So many hard problems. Naming a company. Interesting. Alright, oh wow. So many hard problems. Anyway, so we are going to have a hard problem. That is okay. That is okay. You do them all, and then you feel less intimidated by the hard problems. Hard problem is just a problem. You just think of two medium problems jammed together. Unless it's a problem require special algorithm that you just don't know. Okay, we've done this one before as well. Short encodings of words. A valid coding of an array of words is any reference string S, an array of indices such that words.length equals indices.length. The reference string S ends with the pound character. For each index, the substring of S starting from indices I and up to but not including the next this carries equal to words I. Given an array of words, return the length of the shortest reference string as possible of any valid encodings of words. Alright, reading this through, I don't understand anything what it's talking about. I have to read it again. Okay, so we have a bunch of words, and the encoding is a string, okay, and an array of indices, such that, so we have three indices, right, and then the reference string S ends with the pound, okay, ends with the pound. For each index, okay, indices I is the substring of S is our reference string, starting from indices I, and up to, but not including the next pound sign. And then is equal to words I. The thing is, because me is included in time, so we can say 0 to this, that's time, 2 to this as me, and 3, 4, 5 to this. Nice, that's very good. Okay. What do you think? What do I think? I don't think of anything. What do I think? What do I think? Well, the naive solution is just put all the words together, put a pound sign in between, right? But we can do better. Why can we do better? Is because is that the only way to do better? Is because words can overlap, right? If all the words do not have overlap, which means if a previous word's suffix does not overlap with the next word's prefix, then there's no way we can reduce the encoding. And just to show that, it will be good to run an example. And we don't really need to return anything, but we can just do an example. So instead of saying me, let's make sure they do not overlap, right? If they do not overlap, it has to be, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 11, 12, 13. Yes, so overlapping is very important. And if we do have overlap, I mean the maximum overlap will be this. We have time, we have bell. Then all we need is 9. Wait, what's that? Oh, I can't even do that, but it's fine. This is still, it's an 8. Wait, hold on, it's 18. Oh, That's prefix. My bad. Okay, so why is this 18? So apparently these cannot be, and this is EL. That's not. This is just the whole thing. This is just the whole thing. So we have to be, the suffix has to be equal. So suffix me, and we don't have it. What if I just like time? This is a time. Then how do you differentiate time? Interesting. Very interesting. That means we must put a pound sign at the end of each word. There's no like for the first word we have to put a pound sign here. Otherwise we cannot differentiate. So which means if the second word is the suffix of the previous word, which means if the second word is the suffix of the previous word, then we can put a pound sign in the same spot. And this one will be 10, right? This one will be 10. And there's no way, like even if we have BE, it's not gonna work, because we have to have a pound sign here, right? We have to have a pound sign, but if I have a pound sign here, then there's no point. So these two, even if they're matching, it's not gonna work. So this one will still be, and this one, this also doesn't work. So this is just 1, 2, 3, 4, 13, 14, it would be 15. This would be 15, 16, right? So what's the observation? So the only saving we can have, again, we have to have a pound sign at the end of each word, right? So a pound sign is inevitable at the end of each word. So the only chance that we have to reduce is if the current word and the previous word's suffix equal to the current word. If the current word has anything extending beyond, like if it's not the same, then it's not going to work. Right? They have to be the same. So we grab, each word is what? 7 in length. So we have the first word and the second word, and we just try to see if the current word, isn't that deterministic? We just go through and see which ones we can combine, right? If we can combine, then we go to the next one, which means if we have, let's say, this, so this is combining, and this is also combining, so this one will be 5 because they have the same suffix. I shouldn't say the same suffix. This one is the same. This one is the same. Okay. So what do we say? We grab the current word, right? And then if the length of the current word is longer than the previous, then there's no way, right? There's no way that they can be combined together. No. Why? Happy time. Look at this. This shall be 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This shall be 10 because, it's fine. How about that? Pi time, right? Pi time. So that's what? At 6 or 7. This one will be 7. Yes, this one is 7. What does this tell me? They have to end on the same in order to work. And what if what if we have something in between? Does this work? Well, if we have something in between, and we have to go indices. The first one we have to end here, the start to whatever, and the second one we have to start here. The third one, no, this just won't work. This one will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This one will be 14. I'm marvelously wrong. 9. Well, how does this one work? Oh. It doesn't matter the indices. So we can just say like pi time pound a pound, right? That's 6, 7, 8, 9. Because all those, I see. So in other words, we don't really care where they are. We just want to find all the, and once we build the try, we just need to find the longest length of the try. So as we build the try, we can yeah, so every time we try, we keep going, and then we have the new thing, and that's when we record. We record the length. How do we record the length? What will be the last one, right? So with the last one, we have the length. And then now we move on to the next pass, and the last one is the length. So what we need to do is to figure out a way to put the length, somewhere. How do we do that? Well, every word we can keep track on the length. If we start from something, right, and then we diverge, Okay, so we start from something, and then we diverge. What if I diverge? And if I diverge, then the saving, do I have savings if I diverge? Hold on, let me think again. We have something and something, and I have another thing we end, so we have two words that ends at the same thing. That does not work. If two things end at the same, that we cannot create anything out of it. So the only time we can create anything is if it's a one path, if it's a single path, right? If all the words on a single path, they can be combined by one word. So we're gonna have a try, right? So each path on the try, we just want to find the longest path on this path, the longest length of the path, and then we need to add all the paths together. So now for each path, we keep going, right? And then we will record. Not really record. We just keep something, right? We keep track on the length of the word, and then it will keep going to the last one, right? And then we're basically just saying, if it exists, we're gonna set up a flag. We say if it exists, right? So we go here, and then we say if it exists, then means we have handled it already. What was the best way to handle this? Now the best way to handle it is just don't handle it. Hold on, come back to it. coming home.
Thank you.
Yeah.
It's on your way.
Yeah. I've done it before.
Mm.
Huh? Tell me what toothpaste you need.
Jimbo's food.
Jimbo's what?
Food.
Yeah. I get both.
Are you using credit card?
I use my father's card.
You sure?
Yeah. Tell me what toothpaste you need.
Anyone.
Hmm?
I don't care. The cheapest one.
Well, I have to go home first and then go. Because I will have the food in me.
Then I'll go. Yeah, it's not on your way anymore.
But I can just drop the food and immediately go. It's easier to go there on bike.
No.
Yes.
This is the last half a half.
Messy. Messy boy.
Yeah, try 1.5 layers of dry toothpaste.
Okay. 1.5 it is.
Mm.
I'm back. So we have an idea, right? So basically, we want to find the longest path as we build the try. So what we can do is at the end of the word, we will check. We'll set up a special character to indicate the end of the word. So we'll check if that one exists. If that one does not exist, that means we are. Actually, I just realized this is actually not right. If that one does not exist, it could be during the path. It could be it's a new path. Okay, so we have to put that one down, but we set a different value. Let's say set a negative value. Right, so if you encounter negative value, that means you're still inside some other word, so you don't do anything. But if you hit a value that is a positive value, that means it's a previous longest path. So you deduct it from the original, right? And then you deduct that from the original, and you deduct that from the original. Interesting. You deduct that and a 1 from the original. So every time when you add, right, so if you're on a new path, right, there's nothing. So you put it and you add it. What if it's the first path that you're doing it? Dang it. Let me think again. As you go down, right, you never encounter and how do I know? You're saying we have to check. Well, technically we can. We can check the length. Let's see how many keys we have. Right? We can check how many keys we have. If we have no keys, then that's the first. Right? So I mean, at the end, we always put down a pound sign to indicate that's the end. So the next one going. So at the end, we put a pound sign, and then we say, okay, that I am the longest. Yeah, we can do that. I am the longest, right? So we put the value in, we also plus 1. And then the next one coming in. And as we go through, we find, yeah, as long as we go through and then we find a pound sign, we remove the value and 1, right? And then we also remove the pound sign. And then we're trying to build a new one. And if we, as we go along, we never found a pound sign, and we always, at the end, when we end, we check the length. And if it's nothing, then I'm the longest. Okay, this might work. This might work. All right, so after a lot of planning, I think we are ready to move on. Let's do 19. Okay. Should be 20. All right, let's do this. So try equals lambda. Okay. Predict try. Okay. Then we're gonna build a try. We're gonna have the res equals 0. Okay. And then word in words. Right? And then we're gonna say for each word node, we're gonna have a root. I equals root for I in range len would minus 1, right? Okay, and what do we say? Would I, the letter, right? We basically say and then the length will definitely be at least 1. Okay, so yeah, so you say node would I no, actually it's going to be node equals this, and then we say if, let's put this in node, right? If this is in node, then res minus equal to node this plus 1 and del node this. If not, just keep going until the end. Until the end, when the check, right? Say if, let's say len node is, well, if len node is equal to 0, which means we don't have anything. This node has no keys. If they have some keys, that means we have, it's not the last one, but if it's equal to 0, then we say node star, okay, equal to len would, and res plus equal to len would plus 1. And blah 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 blah. Once we're done, we just return res. That's it. Seems to be too good to be true, right? Okay, we have actually a lot of test cases earlier. We just tried. Should have just kept track of all of them. We also did something here. What did we do? With AP. All right. This one is, I don't remember. Should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think this is a 12. No, that's not. It's this. I tried to say bell. Time bell. That's the one. We cannot say time bell. That's like 14. Something like that. If I remember correctly. 14 or 16. 18. 18. Alright, so we have a plethora of examples. This is minimum length. This is words. Try it. Yes. So it's likely that we have found the right solution, and we are going to go for it. Let's see. Yep, one shot. So I consider this as better performance. Last time we are stuck a little bit, but got it. Yeah, well, it took us like half an hour today too. Oh, but I don't know how long it did before that. 8:28 in the AM. What is March? Is that a Saturday or Sunday? Why would I do it early in the morning? Oh, I know why. That's early in the pandemic. I usually do this in the morning. I remember. Yeah, we kind of shift the time completely. And now it's this. Okay, so what we do is we're going to go into this. Let's take a look at how it was resolved last time. I am pretty sure it's a similar idea, but we'll see. So this is 820. The shortest encoding must use the maximum suffix matching. That means we must group the words together if they have the same suffix. Actually, yes, if they have the same. Not only that, okay, actually, two words can share the same, and that's the only time that they can do this. Otherwise, they cannot share. Like if they match something, but the other part doesn't match, then they cannot share. Right? It cannot share. So that's the only chance. So the problem is converted to build a suffix trie and add up the length of each path in the trie. Yeah, that would be it. So we say on, where n is the total number of letters in words. That's why it's 2000, and with what, like 2000 with 7, so it's 10 to the 5th, right? It's like 14,000, 10 to the 5th. No, 14,000, not 10 to the 5th. 14,000 is 1.4 times 5. 10 to the 4th. Huh, 10 to the 4th. And it's still that slow? Yeah. It is on, right? Yeah, we go through every single character. Anyway, doesn't really matter. Okay, so I want to see. I want to see my current solution, and this is the previous solution. 33 test cases. Okay, this is the try. Duplicate, remove the duplicates. Okay. The heck is this? Forwarding this when I reduce. Last try node. Oh yes, that's exactly what we want. The last try node. And then reduces, this is the lambda, right? And this is the item, the first one. Wait, hold on. Reduce, the first one is the function. And then this is the function, this is the list of stuff, and this is the first value. So basically, the first value go into this, and then we get one out. So get item, try, and we get this one out, and then we have a new value, which is the next node, and then blah 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 until the end, and we get the last node, last try node, And then we're going to say for each node, if, and then because if it is the last node, then it's empty, right? So if not node, those are empty nodes. And then if we follow the same for the I, and then we get the length. Ooh. Oof, no, now we know this trick. Actually, it's right. The T shall be capitalized. But anyway, we know the trick. But Lord, look at this reduce. Look at this reduce. My. 36 test cases, so slightly more. Slightly more than last time. And I have to use a little bit trick here to or delete. Yeah, it's kind of heavy, right? It's more complicated here, but all I need to do is to collect the last node. That's all we need. And we can also remove the words that's duplicated. Yeah, I wanna try to write it myself. Wow, this is just amazing, right? Amazing. But I think in my current one, I'll leave the duplicates in there. That's fine. Unless it's gonna cost a lot, it should be fine. Let me just do so. This is the amazingly short solution using try and reduce. I'm pretty sure I have to use reduce. From func tools, I have to import reduce. Alright, so what we do is last try node. No, hold on. First of all, try equals lambda, default dict try, and root try, and then last nodes equals this for word in, I'm going to choose for W in words, okay? W in words, I'm going to reduce something, dict dot get item, and then the list. The list is this, right? That's the list. And then the first value is going to be root. So root get item, call get item with the first value, and then this. So root get it's that. So we get blah blah blah. Okay, that's that. And then we return sum for I and node in enumerate last node if not node. If not node means that's the last node. Actually, this one we're going to say if a node in last nodes is an empty node, is empty, right? That means it is the last node of the path. So if we do this, and we just say len words I plus 1. Okay. Run it. Holy guacamole. How good is that? Hey. We cannot handle. Ha. 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 Oh. I thought it's fine. We must we must okay, so that's the non-dupe words and the words non-dupes and that shall be 5. Yep. 38. Let's make it clear. This setup requires that the input has no duplications. Timing-wise, doesn't really matter, but it's just the ideal of using reduce to find the line. That's a little trick. Something interesting. All right, so we don't have much time, about 20 minutes. So let's just take a look. What the hell is this? Check if there is a valid parentheses string path. A parentheses string is a non-empty. Hold on, the cat is meowing. Parentheses string is a non-empty string consisting only of left and right parentheses. It is valid if any of the following conditions true. It is left and right. Right. Left, right, yeah. It can be written as AB or it can be written as this, where A is a valid parentheses string. Yes, so you're given, now we know parentheses string to check is using a stack. That's what we know. So you're given a matrix of parentheses. A valid parentheses string path is the grid. In a grid is a path satisfying all of the following conditions. Path starts from the upper left cell. The path ends at the bottom right cell. Path only ever moves down or right. The resulting parentheses string formed by the path is valid. Return true if there exists a valid path in the grid. Otherwise, return false. If there exists one valid path. Two possible paths, okay? And this one is not possible because the first one is wrong. Constraints 100. Okay. Isn't that just to 100 times 100 is 10,000. So even if we brute force it, I mean, we don't have to brute force it, but we can do DFS, right? We can DFS with memorization, a cache. Basically, we say starting from a certain node, if it's true or false, right? So we start in front, we say we can go right, we can go down, all right? And then basically we just call this and call this. And if it's true, return true. I don't know, is that it? That's 7. Man, so every day I try my best to use Vim, but sometimes it just so hard because it's just not like something. It's not like I don't remember or anything. It's just like what the hell happened right now. It's more. It's easier. Something like if I'm in this mode, right? If I want to move around, I have to exit and then move around. If I use the left and right, it's just so easy. And also there are something like the tab stuff, that the tab key is easier to use when I'm in insert mode. Just like these type of things. And I don't want to use the up, down, left, and right, but that's just so natural for me. Up, down, left, and right. It's like I have left and right is index finger and ring finger, and up and down is middle finger. It's much easier for me to navigate compared to HJKL. So I don't know, but I'm still trying. I'm still fighting this. Okay, so what is your idea? Oh, my idea for one. I mean, this is absolutely godsend, right? Import what? Audio cache. Right, so we're gonna cache this. Yeah, I absolutely love this. The quick move. Okay. All right. So, what do we say? We say if we need to have mn will always be larger than 1, right? Yep. So now what? Now we say if I equals n minus 1 and j equals n minus 1, then return true. Otherwise, we go right and we go down. And we say if I is larger than m or j is larger than n, then false. And then we say dfs I plus 1 j. Can we just say return this or dfs I j plus 1? So we either go right, the j plus 1, go down I plus 1. Oh, the valid path. I need to check the validity. Oh, that's difficult. What the hell are you doing, man? It's like whether we can reach the end. Of course we can reach the end. Is when we reach the end, is it valid? I see the difficulty now. Is it valid? I see. Yeah, this is wrong. This is wrong. What am I thinking? Is it valid? Like you can say this is not valid, but with this it becomes valid. And there are just so many paths. What is a brute force? You want to try brute force? Brute force is here, then we just check. And there's no cache. Let me think. An easy way is to count how many left parentheses and how many right parentheses. The left parenthesis must be larger equal to the right parentheses. So the difference between the two must be larger equal to 0. Whenever it hits -1, that's the end. It doesn't work. So with that in mind, as we go through, right, we can keep track, and whenever it drops down to smaller equal to 0, smaller than 0, then we just exit it. It's just going to return false. But that's still brute force, right? We're trying to go through every single one. But what if we can find the count? Right? So what we want is, at my current, I have my value, right? And yeah, so when I land up on the cell, I'll have a value, and that value must be larger equal to 0. And then I go DFS, this one. What am I looking for? Right? What am I looking for? I am looking for a negative. So everyone, when DFS want to return, well, DFS can return, let's say, a set of value. Okay, DFS can return a set of value. So when I'm at, and then return a set of value, and just say if it's in there. If it's in there, we'll just return true. Boom, done. If it's not. So I'm going to slightly change this, right? So it's not a Boolean value. I'll say this is a set, okay? I'll say it's a set. If this, set of integers. Are you sure? Then I have to go through every single one. Then I have to go through every single one because I need to update where I am. So that could be O(n) to the third. Yeah, because what we want is we want to find if there's a 0 in it, right? That's what we want. Okay. Okay. So we want to try? Do you want to try? Do you want to try? Yeah, I want to try. So this one, just return, say 1 if grid ij go to the left parentheses else -1. And it's just going to be empty. So what we're going to do is s1 equals this, right? And then this one going to be s2, this, and then return s1 plus s2. I think we have plus, not 100% sure. right? And then b equals, I don't know, let's say 1 to 4, right? A plus b. No, I have to say union b. That's unfortunate. So we have to union S2. Not really. Not really. So S1 is this, S2 is this. It's not S1 union S2. It's it's my God. Set, right? Say for P in DFS I plus 1 J, and then let's say current value shall equal to, that's oh no, what did you do? I want to go 14, find this, and the whole thing go up. Actually, it's not a whole thing. It's this, and we're just gonna return current. Okay. So for here, we're gonna say P plus current, and this dot union what? Union set Q plus this Q in DFS IJ plus 1. Right? And then we are going to turn this thing. Right? So this one union this one. And we're going to return 0 in DFS 0, 0. Of course, we can say if grid 0, 0 is equal to a reverse, then it return false. Otherwise, we do this. I think this one's correct, but we have a high chance of timing out. If we time out, then we're gonna call it a day because it's over 1 hour. Man, this is so important to not overdo it because you get suckled into this rabbit hole and never get out. Actually, to test the accuracy of this code, I have to comment out this thing. We have grid. This is a has valid path. Max size. List out of where? Ooh, we do this. Ooh, what? Equal to, what the hell are you doing, man? I don't know, man. It's just okay. In this case, I will go into comment everything. I can run the code, which apparently will be correct. Let's see if it's going to time out. I think it's like 0 to the third. Hey, we did not time out, but we had a wrong answer. That is interesting. Don't be too. Oh. I was about to say, don't be so big. Expected false. Output is true. I think we run into the issue. No, I know. We're counting them. That's not the thing to do. What we want is the difference, right? But the difference. Yeah, I know why this is wrong. Like in this case, the right, left will be counted as true. Like seriously, why will this one pass? It's just gonna be -1. Interesting. What's DFS 0? It's 1 and -1. Wait, hold on. How is this 1 and -1? Oh, it is 1 and -1. Hmm. Think again. Hmm. Nah, this is not working. Maybe just brute force it. How would you brute force it? We just check every single path. But again, you already checked. That's the thing, you already checked. I don't know. Let me just write a brute force, and then if it times out, then it just times out. And this brute force is not going to be cache. I don't think it's cache for brute force. And this one is just going to be boolean value. And we have to have a path. Not a path, but a stack. And then, yeah, we don't have to worry about this. And then if I say this, return len stack, right, is equal to 0. If it's 0, then I'm gonna say if yeah, we don't have to change the stack for the last one. And yeah, the last one has to be a right parentheses. It cannot be a left parentheses. So actually we have something more to say here. You can say if this is all, say grid -1 is equal to a left parentheses, then return false. Is that the end is a left parentheses? No, it's a right parentheses. I'm going to return this one equals 1. If we have 1 in the stack, there must be a left parentheses, and now the last one's a right parentheses, then we know it match. So it's going to be true, right? It's going to be true, okay? If that's going to be 1. Otherwise, then we just say the current one, I'm going to push it in. Right, I'm going to say if stack, not if stack, if grid ij is equal to left parentheses, wait, what if it's a right parentheses? So whenever it's a right parentheses, then we just return false. The path doesn't work, right? If it's a left parentheses, we can just count the number of left parentheses. Might be able to just say count, right? When it just be count, it should be 1. If this, then count plus equal 1. Now I don't even have to do that. Yeah, if this, count else, if it's a right parentheses, elif count is larger than 0. Count minus equal, right? Ooh. Hold on. If it's this, then if one of them is true, then we return true. Else return false. Okay, so if dfs plus 1, ooh, we can say if I is larger equal to m, or j is larger equal to n, we're going to return false. So j or dfsi j plus 1 return true, otherwise return false. Okay. And now we say if count is larger than 0, oh, an account. So count plus 1. Count plus 1. Now, this, if count is larger, you go to 0. We don't have to. We don't have to. We can say this, or at any time, or count is smaller than 0. Return false. So now we don't have to do this. Current equal to 1 if else minus 1, right? And then you can say count plus, I don't like this one, C. Plus C, right? Plus C. And then we just return DFS. Is that right? Missing one requirements. Of course I'm missing. So there's a number. So 0, 0. First one coming in. Count. Should be previous count, right? Since it's 0. Okay. It's very important. Let me track this one. Shall be false. I remember it's false. Yeah, timeout. What if we also say, you cache this thing? Ooh! So it's a 3-level, it's a 3-level cache. Oh, this might work. This might actually work. This might actually work. Booyah! It worked. It freaking worked. Wow. Okay, so a little bit summary. All right, a little bit, just calm down, a little bit summary on this. So what happened is we are using a very simple thing here. At any cell, whenever we do caching, right, we'll have to ask at any cell, what is its state? Now, I and j naturally is the state of a cell, but here we have another state, and that state is the count. The number of left parentheses up until that point, right? So that is the state. That's the unique state. Therefore, it's a 3D dynamic programming. And in fact, what is dynamic programming? It's just to iterate through all possible states. And in here, we just have the states. And we know if it's outside, it's going to be false. And the count smaller than 0. This is very important. At any time, because we're going from the top left corner, we actually just counting the path. This is a representation of the path, right? Just how many left parentheses are left. So every time we have a right parentheses, we'll cancel out one of the left parentheses. And in fact, when we do this, it is absolutely true. Yeah, it's fine. We can use this. It's okay. It's just at any point, right? We need to see if the count is smaller than 0, which means there are too many right parentheses already, and that gotta be false, right? So it's false. Otherwise, the last one, we have to have 1. Otherwise, it's going to be false. And this is the current, and we just do this. Straightforward, right? Very straightforward. Very, very straightforward. Wow, this is great. Very impressed with myself. Didn't expect to solve this one, but fortunately we did. It's a 3D DP, right? We need to ask ourselves in DP problem, what is the state of each, what constitutes the state? What is the state of each function calls, right? Each DP calls. Now in this case, I and j are naturally the state because they represent a unique location, position, right, on the grid. In addition, we have the count of the left parentheses as the state, because when we reach grid ij, we can come from different routes, and these routes can be represented by the number of left parentheses left. And if at any time, right, if at any time the number of left parentheses drops below 0, that path is invalid immediately. Otherwise, we carry on until hitting the last cell. And parentheses at that moment must be 1. And that's it. We use value cache to simplify the memoization process. Simplify the process, yes. So I think the runtime is OMN for sure. And how many different counts do we have? M plus n. OMN m plus n. The maximum count. Different count. And we run at this, which is not bad. All right, so let's go to discussion. DFS 205, yes. The same idea, right? The same idea. So it's not that difficult. No, it's not. It's not that hard. What should I say? All I can say is this is a tough question, but I think don't have fear. It's obviously the number one thing. If you got fearful of them, definitely not gonna do. Yep. So don't be fearful, and then in my mind, just a hard problem is just a combination of medium problems. And if we can solve medium problems, theoretically speaking, we can solve hard problems, majority of them. When there are hard problems, they just require tremendous ingenuity and or some type of algorithm we just don't know, then we just can't do anything. But a problem like this is just a combination, right? It's a combination of DP, a combination of DP, DFS, and find a value of the parentheses. It's a combination of the three. You just need to find a way to stitch them together, and then it shall be good. And one more advice: you have to solve problems when your brain is fresh. That's so important. All right, that will be it for today. I think we did a good job. I'll see you guys tomorrow. Adios.